Okay, we're looking at session 5 here, starting out with some fraction bars to talk about equivalent fractions. Um, we are going to use our blue bar as the whole, okay? And then we are going to show some equivalents with some other colors. So again, I know that this is not going to be perfectly even, but let's see if we can kind of get a general idea of what we're doing here. So we're starting out with the blue bar, okay? So we have our blue bar. And we know that in comparison to this blue bar, if we were to compare 5 purples, 3 oranges, or 6 pinks, we would end up with an interesting pattern here, okay? So let's start out first and let's draw the oranges, okay? So if I want to draw the oranges to represent this, okay, tells us we have 3 orange. Okay, so that's about what my 3 orange are going to look like. If I were to put down my pink blocks, I would be looking at 6 of these. Okay, so 1, 2, 3, 4, 5, 6. All right. And then 5 purples would also consume the same amount of space if we were to break this down. Okay, so yeah. All right, so let me look. I may have. All right. So there's my 5 purples, 3 orange, 6 pinks. And it asks us it tells us we know that these are equivalent, and it wants to know how the fraction bars demonstrate this. If we were to lay this out, what's the pattern that we would notice? We would see all of these combinations of strips would be the same length. When we're using a length model in fractions, length is representing worth, okay, or value here. Just like if we were using circles, the area that it covers would be representing that worth or that value. So length is what's going to demonstrate that, okay? And then it asks us in part B, using the same fractions, okay, how would we use a set of counters or set manipulative in order to prove that, okay? So let's go back, and I'm going to kind of undo what I just did there, that separation of the pink. And I'm going to give myself some more space here, all right? So what we want to show, obviously, if the blue bar is a whole, what we're going to notice is that all of these fractions represented 1/2. Okay, we know that we had 5 purple, so there must be 10 fractions altogether. So we know our 10 pieces. So we know our purple is showing us 5/10. Okay, so if we go back to our orange, looking at it, we know it has to be showing us 3/6 if the blue is the whole. And if we go to pink, that has to be displaying 6/12. Okay, so wants to know, how can I use a set of counters to demonstrate that these fractions are equal? Okay, now we're going to have to do that using groups. And using groups and counters is one way that we can sort of illustrate the idea of common denominators. Okay, all of these fractions are equivalent: 5/10, 3/6, 6/12. All of them are 1/2. Okay, if we were to simplify these fractions to 1/2, we could do that. I'm not going to be able to do that with counters, though. If we simplify them to 1/2, then it would be, very easy to just show 1/2. It's not exactly what this question is wanting. It's wanting to know how many counters would I need to use in order to produce 5/10, 3/6, and 6/12, all out of the same set of counters. Okay, so that's what's unique about this. So let's start out with this. Let's say I used 12 counters. Okay, that's fairly reasonable here in terms of looking at this. If I were to use 12 counters, I would be able to adjust this in terms of 6. I could regroup that. I could move forward. I could do whatever would work in that pattern. So let's kind of look at this and let's think about if my pinks are 12ths and my oranges are 6th, okay, and my purple are 5 or 10ths, then I'm really going to have some sort of a value that can be grouped into equal numbers of sets here. Okay, so let's just kind of think about what kind of a common denominator would we be looking at here. All right, so in 10 we have factors of 2 and 5. In 6 we have factors of 2 and 3. We've already used 2, so we'll add the 3. And in 12 we have prime factors of 2 times 3, or 2 squared times 3. Okay, we already have one factor of 2. We already have one factor of 3. So let's add another factor of 2. All right, so if we're looking at this, we're looking at 10 times 3 is 30 times 2 is 60. So if we use 60 counters, we should be able to replicate all of these groups. Okay, so let's start out with the tenths. Okay, so I have 60 counters. I want to replicate 5/10. Okay, so I'm going to make 10 groups to replicate each one of those tenths. Okay, so if I do that, automatically, okay, then I have to have 6 in each group. So I'm going to color these purple the first time around so we can see that 60 counters is going to work. So we'll start with our purple first, and I'm going to give myself a pretty good size box here. All right, I'm going to create 10 groups. Okay, so 2, 3, 4, 5, 6, 7, 8, 9, 10 groups. Okay, each one of these groups is a tenth, and so forth. All right, now 5 of these groups we're going to color in some way to represent the 5, and the other 5 will be unrepresented to represent 5/10. So let's think about if we did this, if we had to have 10 groups and had 60 counters, we had to break them in 2. We should have 6 in each group. So that's what I'm going to do. I'm going to put my 6 counters in these 5 groups. Okay, so I have 4 groups, one more. Okay, so there's 5 groups. I know over here I also have 5 groups. So remember, these counters are 2-colored. The ones we have in our kits are red and white or red and yellow. So I'm going to have another 5 groups of 6 counters. The only thing is I would flip them over to the other side. Since we don't have purple counters here in our group, I'm just going to use black, which would represent the other color in this case. Okay. Now, sometimes I hear the question of, well, how would we have known to search for a common denominator? Well, it really should become common sense. And the thought behind that is if you're going to have to make groups using a number of objects that you can make groups with this one, and this one, it would have to be some common factor. Okay. 60 is not the only common factor of 6, 10, and 12. I mean, we could have 120 times 6. Okay, that would also be a common factor of those, but it would obviously not be efficient, especially if we're going to be grouping counters. So if I know I have to be making groups of 10, groups of 6, and groups of 12, it should make sense that whatever number of counter I choose is evenly divisible by those numbers. If it's not, I'm not going to be able to make those groups appropriately, okay? So again, you might not have thought of it as a common denominator you would normally think of as part of a process, but hopefully once you start thinking about the fact that you have to make groups based on those numbers, it should be a logical next choice that whatever number you choose must be broken down. Okay, so now my orange ones, I'm going to have to make groups of 6. Okay, so here I'm going to represent my groups of 6. Okay, so 1, 2, 3, 4, 5, 6. So I'm representing 6 here. And I want 3 of my groups to be one color and the other 3 to be the other color. So I have 60 counters here. I'm going to break them into 6 groups evenly. So I should have 10 in each one of these little groups. Okay, so I've got my 3 groups there that are all orange. And remember, we have 2 color counters. So I'm going to use the black color to show the other groups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have using 60 counters, but we've put them into 6 groups with 10 in each one. And we've represented 3 out of those 6 groups with a different color, okay? Last but not least, we've got to make the 12ths, okay? So we're going to now, and I'm going to try to put some space in here. Excuse me. So I can draw this last box. All right, I've got my pink counters. I'm going to pink, and then I'm going to have to split 60 counters into 12 groups. Okay, so I'm going to stretch this out a little bit just so I have some room to draw. Ideally, we'd want these to be the same hole, but I'm just expanding to give myself some space to write here. Okay, so there's 6. Should have 12 groups here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so now I've got 60 counters, 12 places to put them. If I were a student or if I were teaching a very, very young student, I might actually encourage them handing out the counters one at a time into each group until they ran out. Hopefully for us, though, we should recognize that there would be 5 in each group. Okay, so I've gotten 4 groups. We need 2 more. 2, 3, 4, 5. 1, 2, 3, 4, 5 counters. So at this point, okay, I have 6 groups out of 12 that are one color. And then again, I would use the other color on the counter and represent the other groups. Okay, so here's my other 6/12. Okay, so I've represented essentially the same worth. I've represented 1/2 using tenths in the purples, using 6 with the orange, and using 12 with the pink. Okay, now we're moving on down to part 2, where it wants us to express each fraction in lowest terms. Now, I'm hoping that when you did this, that you did not attempt to, take forever going through this process by trying to divide out what you see. Okay, that is a possibility. But again, like we said, prime factorization will help us if we express each value in its prime factors. Okay. We start out with 144. Automatically, I know this is an even number. So if I did that, I would be looking at 2 times 72. Okay. And then 36, 18. Okay. So in the numerator here, I'm looking at 1, 2, 3, 4, 2 to the 4th power times 3 squared. Okay. And then I would consider the denominator. Okay. So I have 60, 2 times 30, which would be 3 times 10, which would be 2 times 5. So in the denominator, I have 2 squared times 3 times 5. Okay, now when I look at that, I have 2 factors of 2 that can be canceled out. Okay, and then I have 2 squared left in the numerator. I have 1 power of 3 that can be canceled out. And then there isn't much I can do with 5. Okay, so if I look at this, I have 2 squared, which is 4, times 3, which is 12 fifths. Okay, and notice this is an improper fraction, right? Now, we know, okay, that 60 divided by 5 is 12, and then 144 divided by 12 is 12. Hopefully at this point we've figured that out. So I have it expressed in simplest terms or lowest terms. Okay, keep moving on. We could, we don't have to do it this way, but it does necessarily work. I'm not exactly sure what happened here. Let's go back, hopefully. Let's go to view. Okay, there we go. So let's move down here to looking at 90. Okay, so here I would have 3 times 30. Okay, and 3 times 10, 2 times 5. So in part B, I have 3 squared times 2 times 5 if I factor it. And then when I look at 165, I know it's divisible by 5 for sure. Okay, so that would be 33. Okay, and then 3 times 11. So 5 times 3 times 11. All right, so let's think about what we can cancel out. The 5s take each other out. We've got 1 power of 3 that's gone. So we have 3 times 2 over 11. Okay, and that would be 6 elevenths. Okay, so if I'm looking at this, okay, if I'm trying to know for sure if I have done it correctly, I can always try to find whatever, the greatest common factor was. And I can consider multiplying both of those by the greatest common factor, which should produce 15, okay? Because 165 divided by 15 is 11. 90 divided by 15 is 6. And how should we really know that? We look here. We see that 11 ended up left. So this was the other common factor. Okay, let's keep looking at this. We've got 320 over 240. So 320. Sometimes even numbers can be a little bit of a challenge. For this one, I might start with 10 and 32. Might kind of speed up the process here. Okay, so I'd have 2 times 16. And here I would have 4 times 4. And 2 times 2. So what I'm looking at, if I'm looking at all these prime factors, okay, I'm looking at 1, 2, 3, 4, 5, 6. So 2 to the 6th times 5, okay, in my numerator. And then I can follow the same process for the denominator. Okay. Start out with 2 just to make this an easier process. Okay, 5, 12, 6, 2, 28. I may need some additional space here, so I'm going to kind of scoot up. So 2 and 64, okay, which would be 2 and 32, and 2 and 16, and of course 16 would just be 2 to the 4th. So when I count this, quite a bit of 2s. 1, 2, 3, 4, 5, 6, and then we have the 2 to the 4th here. So it would be 2 to the 10th in the denominator. Okay, we don't really have anything else. Broke down to factors of 2. So if we're looking now at what's remaining in the particular fraction here, we've got 6 powers of 2. So we end up with 5 over 2 to the 4th. Okay. And again, 2 to the 4th is 16, so we should have 5/16. If we wanted to check that, we could think about 320 divided by 5, which would be 64, okay? And then 64, of course, times 16 should produce 1,024 if we wanted to check. But it is a good way to kind of get the idea of why we simplify, what we mean by lowest terms, taking out common factors, okay? So now we have a question that asks us, is a fraction a number? Okay, it is a comparison of 2 numbers. It is a ratio, so we have a comparison of 2 numbers by division. It is particularly a part to whole ratio. And we say, why do we say fractions are equivalent rather than equal? Because they're not exactly the same, okay? When I say 1/2 and 2/4, these are not exactly the same meanings, okay? 1/2 means I have a whole that has been broken into 2 groups, and I am considering one of the 2 groups. If I have 2/4, that means I have a whole that has been partitioned into 4 pieces, and I am considering 2 out of the 4 pieces, okay? So when we say they're equivalent, really we're just talking, in this case, we'd be considering the area that they cover would be the same as long as they're compared to the same whole. But that's what we mean by equivalent fractions. They're covering the same area. They're covering the same length, okay? They're representing the same portion of a set, but they're not exactly the same in terms of their partitioning, okay, and the size of their pieces. So does reducing a fraction make it smaller? No, it does not, okay? Its worth remains the same. When we hear the word reducing, and I really hate this word, it's one of the ones that's part of my goal to eliminate from math. We're not reducing, we're not making the fraction smaller. We are removing common factors. So we're writing it in simplest form. Okay, so this question, I could kind of see why someone might make an answer for both. True or false? Yes, fractions help fill up that gap, but remember, we also have numbers that are irrational, and those numbers cannot be written as fractions. So if it was going to be me, I would take false for this question, simply because it doesn't address the irrational numbers that cannot be written as fractions, but yet we still find on a number line. So those irrationals get kind of left out by this explanation. Okay, 15 teachers decide to attend a teaching conference, and they decide to participate if at least 3/4 of the group votes yes. Okay, so 12 of the 15 vote to participate. We want to find 3 different ways to mentally determine whether the teacher should attend or not, and it wants us to use fractions, not decimals or percents in this thinking. Okay, so we've got 12 of 15. we want to know if that is going to be equivalent to 3/4 or if it's going to, in some way, okay, be less than 3/4 if we've met that option. So let's start out with our 12 out of 15. And let's try to write that in lowest terms and see if maybe that starts to help us, okay? Basically, one thing we know here, we could go to lowest terms. If we did that, okay, we would be pulling out a common factor of 3, which would be 4/5. Okay, if we factored out that common factor of 3 here, we would be looking at 4/5. Okay, now if you're not sure about how I come to that conclusion, think about 12 factored into prime factors. Okay, you would have 2 times 2 times 3. Okay, and for 15, you would have 3 times 5. 3 cancel out. 2 squared is 4, 5 is 15. Okay, now let's compare that to 3/4. Both of these are one part away from the whole. A fourth is a bigger part than a fifth. So 4/5 is closer to one whole. What does that tell us? It lets us know that 4/5 is greater than 3/4. So yes, they should attend. Okay. Use mental methods to find the smaller fraction in each case. Don't use decimals, blah, 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 blah. Okay, explain your methods. All right, 13/8 are 1 4/6. Okay, we know that both of these have one whole. Okay, so let's kind of disregard the whole. That's equal. And let's just think about the fraction itself. So you can kind of forget about the 1 here. If we were to turn this into a mixed number, we would be looking at 1 5/8. So we're going to kick off the 1, and then we're just going to compare it to 5/8. Okay. So we're trying to decide which one of these would be larger. And I know we skipped A. Come back to that in just a second. So let's simplify 4/6 into smallest terms and see if that helps us any. We would be factoring out a common factor of 2, so we'd be looking at 2/3. Okay, 2/3 is 1 value away from a whole, whereas this is 3 values away. So if we doubled it, we were 2 values. What if we tripled it? Okay, that would be 6/9. Okay, if we tripled it. I'm sorry, not if we tripled the other fraction. Let's triple what we actually started with here. If we tripled 4, that of course would be 12. And if we tripled 6, of course, that would give us 18. Okay. I'm not quite sure I had the right value there. Okay. Again, here we're 6 away. All right. So let's try to keep working with this and see if we can get to a value where we're 3 away. If we went back to 2/3, okay, again, if we doubled that, we would be at 4/6. Okay, double 2, we get 4. Double 6, we get, or double 3, we get 6. What if I multiplied this by 3? Okay, 2 times 3 would be 6. 3 times 3 would be 9. Okay, and these should be able to draw that conclusion here. So we're 3 parts away. Here we're -3/9, and here we're -3/8. Okay, 9ths would be smaller pieces, 8ths would be bigger pieces. So this 4/6, okay, that 4/6 should be larger than 5/8. Okay, if we make that conclusion, the 4/6 should be larger than the 5/8. Okay. Let's go ahead and stop here because it's getting to be a little bit of a long video, and then I will put the others in the second session.